to C3 sugar, and we'll see that several times this evening depending on how far I get. And of course this has a name, phosphoglyceraldehyde would be the shorthand name for it, and that's the formula. So all you've done so far is take this big portable high energy sugar molecule, and you didn't let it blow up, make a sugar rocket out of it, because that's the key to metabolism. You don't want to burn the sugar in one step and incinerate the cell. You want to dismantle it carefully, one step at a time, and harvest the energy in little steps. And that's kind of what we're doing here. We're going to take it apart a little bit at a time, only so far it's cost us energy. And so say here's the glucose molecule on an energy diagram, and here's the carbon dioxide and oxygen in water that it's going to turn into later. And so it's a downhill reaction. But in order to get it primed, you've got to build it up to get it to the crest of the hill, and then it's going to crash down. So that's what we're doing. We're rolling this big molecule up to the top of the hill, and from this point on, we're going to be able to harvest some energy from this, but it's already cost us 2. So if we don't have a goal in mind, if we don't have any kind of anticipation, if we don't have what? Telos, okay, plan, future, goal, all of those things, you can't do this one step at a time. None of these steps have any value in and of themselves. It's only if you have some kind of goal in mind. Well, let's take a look then at the second series. So once you get the glucose activated, you split it apart into 2 3-carbon sugars. And this is still one that stuns biochemists and organic chemists, and I don't think we really know to this day what's going on here. Because this looks too good for words or something like that. Here's a 3-carbon sugar with a phosphate on it. Now we got 2 of them. We split 1 6-carbon sugar, we get 2 3-carbon sugars. But if we took that phosphate and made it back into ATP, we'd only be back where we were to start with. So that'd be a waste of time. We want to wind up with more ATP than we started with. Well, if we're going to do that, we've got to get some phosphate in there that didn't come from ATP, so we can use it to make ATP. Well, where are you going to get it from? And the answer is dirt. Okay. By the way, 1/8 of the world's phosphate supply comes from Central Florida, from Bone Valley. By the way, where'd the phosphate come from? The ground up bones of mammoths, mastodons, saber-toothed cats, whales, dolphins, all these fossils that are buried by the zillions in that Peace River Valley. And some of them were buried and preserved, some of them were just ground to powder. But phosphate's a mineral in the ground in various places in the world. And so this is just mineral phosphate, inorganic phosphate, just phosphate that would be included when you eat plants and any kind of mineral nutrition. Phosphate's a real common nutrient, it's not a rare one. And so, and I've still got a question mark on this. Most of the books, I haven't checked just recently, but still lists this reaction here as spontaneous. In other words, there doesn't seem to be any enzyme that does this. There doesn't seem to be anything in particular. But a living cell is going to have a lot of phosphate floating around in it. And I personally think there's got to be more to it than that. But the idea is if you have a 3-carbon sugar with this so-called aldehyde group on the top, that double bond oxygen has a tendency to react. It has a tendency to let go of one of the bonds that hold it to carbon and grab onto something else. So it's a bridge between 2 molecules. And so it has a natural tendency to do that. And apparently, and I think there's got to be more of a context to this than it just happens. But that's all we know right now is this group here just attaches. And now instead of PGAL, phosphoglyceraldehyde, you have di-PGAL, 2 phosphates. Now you got a phosphate on the top and the bottom. And that's got to be a strain on the molecule because it's only 3 carbons long. And the phosphate groups are bigger. They take up more space than the atoms around the carbon. And so these things, are full of negative charges. They tend to repel one another. That's a fair amount of strain on the molecule right away, which makes it kind of interesting that they would stick in there like that, just kind of sneak in. Although keep in mind, I drew them on the same side, but most times molecules have the ability to rotate around. And so they would tend to take the big groups and put them on opposite sides of the molecule. And so there you are. You snuck on another phosphate. Nothing magical, nothing mysterious. By the way, notice, I'm talking creation, but I haven't really said anything about anything supernatural, have I? This is stuff that we understand chemically. It's the process, the pattern that looks created. We're not violating any rules of physics or chemistry in this process. So that extra phosphate's on there. Now we've got some phosphate. We've got enough phosphate. We've got 2 of these molecules. Each has 2 phosphates. We've got 4 phosphates. And so potentially we have enough phosphates to make 4 molecules of ATP, 2 to replace the 2 we already used to pump up glucose, and then 2 to run the rest of the cell. Okay, and you can see why anaerobes kind of, remain bacteria, kind of hang around in the mud. Not a lot of energy, but that's all the energy they're going to get. But how are you going to do that? Okay, so there's a couple phosphates there. Okay, now what happens next? Okay, I could have introduced this earlier, but now you see the second line of evidence for creation. Maybe since I've got different colors, I'll put it in a different color here. In this case, what you have is another example of an evidence of creation. So this will be creation evidence. Maybe I'll use Roman numerals for that. Creation evidence number 2, complex prerequisites. And I could have introduced this term earlier, but I'll bring it up right here. To make this process work, you have to have very complex molecules to start with that require lots of energy to produce. And so in order to make the process go, you've got to have these already there. And so here you have NAD is going to come in here, grab a couple of hydrogens, not just any 2 hydrogens, but it's going to grab 2 particular hydrogens off this molecule with the help of an enzyme called a dehydrogenase. And we see these. There's only a few enzymes in living cells that are used over and over, and kinds of enzymes. They have multiple variants with different specificities, but here's an enzyme that's going to pick up hydrogen. But look who picks up the hydrogen, NAD. Well, who or what is NAD? Well, you can see why biochemists, like the Army, use abbreviations. That's nicotinamide adenine dinucleotide. Okay. And by the way, the N, the nicotinamide, that's a derivative, or niacin and nicotine are derivatives of that. And do you know, if you didn't have certain enzymes in your lung, 1 puff of cigarette smoke would be totally fatal. If you didn't break down this molecule right away and convert it into something else, it would just wipe out energy metabolism in an instant. You'd be dead at the end of 1 puff. Now, as it is, it takes a few years. But here you have, and notice nicotinamide. Okay, this has got a sugar with a 6-sided ring on the top of it with a phosphate bridge over to another phosphate bridge with a 5-carbon sugar.